Now, Chapter 12, Chemical Bonding. Now, because we cannot describe exactly how an electron moves in an orbital, chemical bonding cannot fully be described. But we have a very good idea of what it is. It's a force that holds groups of atoms together and then makes them function as a unit. So this is an example of water. 2 hydrogen molecules and 1 oxygen molecules. Now, what's very important is that bond energy, which is the energy required to break a chemical bond. It is not the energy required to form the chemical bond, that is activation energy. Rather, it is the bond energy, the energy required to break a chemical bond. There are 3 types of bond, and the first type is ionic bonding. This is between a metal and a non-metal. The metal donates 1 electron to the non-metal. So now it is a positive charge being attracted to a negative charge. Covalent bonding is when both atoms equally share the electrons. So you have 2 hydrogens, exact same atoms, but 2 of them. They're going to come together. So we have 1 here, 2 here. They come together and they're going to equally share the electrons between the 2 to form a covalent bond. A polar covalent bond is very similar to a covalent bond, except now we have unequal sharing. One atom is going to want those electrons much more than the other. So here we have HF. And we know that fluorine is the most electronegative atom, meaning it wants to have electrons the most. It's going to attract the majority of those electrons shared by the hydrogen and fluorine to its side. So it has a partial negative, while our hydrogen is left with a partial positive because the majority of the electrons are with fluorine. That is a polar covalent bond. Electronegativity is how bad an atom wants to have electrons, or how bad does that atom attract electrons to itself. So what we do is we look at values on the periodic table and we determine how large of a difference between the 2 atoms is there. If there's no difference, that means we have a covalent bond. Both atoms want the electrons equally. If there is a difference, that means one atom wants an electron more, then we have a polar covalent bond. So the electronegativity is how bad does a molecule attract electrons to itself. So on the periodic table, there's a trend. The top right, so excluding the noble gases, the top right, fluorine, is the most electronegative. That means it wants to have the electrons the most. Then the bottom left, that is those that do not really want to have the electrons. So the top right is the most electronegative, while the bottom left is the least. So the trend is, as you go up and to the right, you get more electronegative. Here is the periodic table with the values, so you can see this trend. We have fluorine with a 4.0, and francium and cesium with a 0.7, the least electronegative. Here is a picture summary of the 3 types of bonds. A, we have a covalent bond, which has the electrons shared equally. B, we have a polar covalent bond, which we have an unequal sharing of electrons, or a difference in electronegativity. So we see the one side is partial negative and the other side is partial positive. Then C, we have an ionic bond, which we have a full transfer of electrons, so we have a positive and a negative, and it's the attraction between the positive and negative that holds them together. So what we're going to talk about here is bond polarity and dipole moment. Now, bond polarity is just the difference in electronegativity. You look at where each atom is located on the periodic table in your bond, and you determine which one has a higher electronegativity. Whichever one has a higher electronegativity, that is going to have the partial negative charge, and our arrow is going to always point to the partial negative. Now, dipole moment, that is when we take all the bonds in a molecule and determine if our whole molecule is going to have a partial negative or partial positive side. So what we see here on the left is the partial positive and the partial negative in the HO bond for water. So if we were to draw our arrow, it would look like this, pointing to the oxygen and the positive. Same thing on the other side, pointing to our negative side. Now with this shows us is each bond's polarity. We have two hydrogen-oxygen bonds, and we draw the polarity for each. Now, dipole moment is we're going to look at the whole molecule, and we see that because we have the two arrows, and the up and the down pointing is going to cancel out, but overall, we see here, it's going to point to the right. And this is the dipole moment because we looked at the individual bonds and sort of added the bonds to get our dipole moment. So far now we've talked about how our valence electrons bond, but now we want to start looking at what types of shapes do our molecules take once those valence electrons rearrange with those molecules. So what's important to remember is that our atoms want to achieve the octet configuration, meaning they want to have 8 valence electrons, or 2 in the case of hydrogen. And there is only one more exception that you need to know, which is boron, and it only needs 6. So keeping this in mind, when you draw your Lewis structures, everything needs to either achieve an octet or a duet, meaning it has 2 or 8 valence electrons. So the first step in a Lewis dot structure is to first bond our molecules together. And in order to bond the molecules together, the two atoms are going to share 2 electrons. So that's these electrons right here in the middle. These 2 are shared by each fluorine. So originally the fluorine only had 7 valence electrons, 7. But when we bond them, they each share those 2 now in the middle, so each fluorine has an octet. This side has 8 electrons around it, and this side has 8 electrons around it. So here are 3 basic rules for writing a Lewis structure. First, sum the valence electrons. Remember, not total electrons, valence electrons. And then we use 2 electrons to form a bond between the 2 atoms. And then we spread out the remaining electrons to try and achieve an octet for each other atom. So here's an example. Water, H2O. Each hydrogen has 1 valence, and then oxygen has 6. So we have a total of 8 electrons. So we take 4 of those electrons, and we form 2 bonds here. So we had 8 electrons, and now we used 4 in bonds, and now we have 4 left over. And what do you think we're going to do with those leftovers? Well, what we do is we take those 4 leftovers and we put them around the oxygen. Now we can check our octet, or in the case of hydrogen, duet rule. So this hydrogen here has 2 from this bond. This hydrogen has 2, so both hydrogens are happy. And this oxygen has 8. We have 2, 4, 6, 8. So we have achieved the octet and duet. Now PBr3 here, same thing. PBr3 has 26 valence electrons. So we took 6 electrons and formed our 3 bonds to bromine. Then we took our remaining 20 and spread them out around our outer atoms. But once we reached an octet on the outer atoms, we still had 2 extra electrons. So we can take those 2 and put them on the phosphorus in the middle. Now that phosphorus, if you notice, now we have an octet, because originally it only had 2, 4, 6 from those bonds, so it needed those extra 2 in the lone pair to make an octet. Here, these are the different types of bonds, a single, double, and triple bonds. And those are just indicated by how many electrons are shared. In a single bond, only 2 electrons are shared. In a double, 4 are shared. And in a triple, 6 are shared. Now, if we have a molecule that has 1 double bond, but that double bond can be in multiple places, we have what is called resonance. So in our first Lewis dot here, we have the double bond at the bottom. Next one, top left. Final one, top right. That double bond can go to any oxygen. So we have to make sure we draw all possible Lewis structures. We have to draw that double bond according with each oxygen, because there's nothing holding that double bond in one specific location. Remember, when you're wondering when do I form a double bond, you form a double bond when you've already spread out. So you've already spread out your remaining electrons around each atom, and you don't have any more electrons to give. You've run out of your valence, but your central atom is short an octet. If your central atom is short an octet, then you need to start sharing a lone pair. So there was a lone pair up here that we shared in order for nitrogen's octet and oxygen's octet to be 8. And here now we have a couple exceptions to the octet rule. One of those, which we mentioned before, is boron. Boron does not need 8, it only needs 6 electrons. And that is the only one that you need to know, along with hydrogen. Hydrogen only needs 2, boron only needs 6.